Chemistry Optional Paper 2, the chapter on polymers, specifically their preparation, structure, and properties, is highly scoring. Questions in this section are typically direct, focusing on reaction mechanisms, structural features determining property variations, and the synthesis of commercially important polymers. Below are selected high-yield questions with precise, exam-oriented structural answers and mechanisms. Question 1. Coordination, polymerization and stereoregularity. During the polymerization of propene. Discuss the structural differences and physical properties of isotactic, syndiotactic, and atactic polypropylene. 15 marks, model answer. 1. Mechanism of Ziegler-Natta polymerization, stereocontrol. Ziegler-Natta catalysts typically consist of a transition metal halide, e.g., text, titanium 1 chloride, _3 or text, titanium 1 chloride, _4, and an organometallic co-catalyst, e.g., text, Al, C, _2, text, H, _5, _3. The polymerization proceeds via a coordination mechanism at the active titanium sites on the crystal surface. Coordination. The alkene, pi electrons of propene, coordinates to a vacant d orbital site on the titanium atom. Insertion. The coordinated propene undergoes a migratory insertion into the existing titanium carbon, text, Tr, alkyl bond. Stereochemical control. Because the catalyst surface is highly asymmetric and sterically hindered, the propene molecule is forced to approach and orient itself in only one specific direction before insertion. This repetitive, direction-specific insertion ensures that all methyl, text, CH, _3, groups are arranged uniformly in space. 2. Structural and property comparison of polypropylene isomers. The configuration of the pendant methyl groups radically alters the packing efficiency and crystallinity of the polymer. Text, CH, _3 groups alternate regularly above and below the chain plane. Text, CH, _3 groups are distributed randomly along the chain. Crystallinity. Highly crystalline, highly ordered packing. Semi-crystalline. Completely amorphous, cannot pack tightly. Melting point, T_M, high, approx 165 carat, circ, text, C, 170 carat, circ, text, C. Intermediate, approx 130 carat, circ, text, C. No sharp T_M, softens at very low temperatures. Mechanical strength. High tensile strength, rigid, tough. Moderate strength, more flexible. Soft, tacky, mechanically weak, used in adhesives. Question 2. Synthesis and chemistry of engineering polymers. B. Give the chemical equations for the preparation of the following polymers, specifying monomers, reaction conditions, and their properties. Applications. Nylon 6, 6. Polyurethanes. Glyptel, alkyd resin, 15 marks, model answer. 3. Nylon 6, 6. Monomers, hexamethylene and adipic acid. Reaction, mechanism, step growth condensation polymerization. An organic salt, nylon salt, is formed first, which is then heated under vacuum to eliminate water. Properties and applications, high tensile strength, abrasion resistance, and excellent elasticity due to extensive intermolecular hydrogen bonding between peptide linkages, text, C = O, C dots, text, HN. Used extensively in textile fibers, carpets, and mechanical gears. 4. Polyurethanes. Monomers, toluene diisocyanate, TDI, or methylene diphenyl diisocyanate, MDI, and a diol, e.g., ethylene glycol. Reaction, mechanism, step growth addition polymerization. 5. Glyptel, alkyd resin, monomers, phthalic anhydride and glycerol, a triol. Reaction, mechanism, condensation esterification. Because glycerol is trifunctional, cross-linking occurs readily upon extended heating. Properties and applications, highly thermosetting, forms hard, brittle, and highly adhesive films upon curing. Extensively used as a binder in paints, lacquers, and electrical insulating varnishes. Question 3. Structure property relationships, glass transition temperature, C. Define glass transition temperature, T_G. Discuss how the following structural parameters influence the T_G of a polymer: chain flexibility, rigidity. Pendant groups, size and polarity, cross-linking, 10 marks, model answer. 6. Definition of T_G. The glass transition temperature, T_G, is the temperature region where an amorphous polymer transitions from a hard, brittle, glassy state into a soft, flexible, rubbery, leathery state. It signifies the onset of long-range coordinated segmental motion of the polymer backbone. 7. Influence of structural parameters on T_G. Chain flexibility, rigidity. Polymers with flexible backbones, e.g., aliphatic CC chains, text, CO, bonds in polyethylene oxide have low internal rotation barriers, allowing segmental motion at low temperatures, right arrow low T_G. Incorporating aromatic rings or rigid heterocyclic structures into the main chain, e.g., polyethylene terephthalate, polyamides, restricts bond rotation, right arrow high T_G. Pendant groups, size and polarity, bulkiness. Large, bulky pendant groups, e.g., the phenyl ring in polystyrene, hinder free rotation around the carbon backbone, requiring more thermal energy to induce movement, right arrow elevated T_G. Polarity. Strongly polar pendant group, e.g., text, CN, in polyacrylonitrile, text, Cl, in PVC, increase intermolecular dipole-dipole forces between adjacent chains. This tightly binds the matrix, right arrow elevated T_G. Cross-linking. Cross-links introduce covalent chemical bonds between different polymer chains, anchoring them in place and severely restricting molecular freedom. As the cross-linking density increases, translational movement of segments becomes nearly impossible, causing a drastic increase in T_G, and in highly cross-linked thermosets, T_G may not even be observed before thermal decomposition. Would you like the mechanisms and questions related to number average and weight average molecular weights, M_N and M_W, of polymers?